This time, we will discuss iteration and recursion. Now, when we discuss loops, we defined iteration as one execution of a loop body. Now, what is a repetitive computation? It is simply a computational task that is repeatedly done or performed finite times. And we could solve or perform repetitive computation by using a loop. And if we are using a loop, then we call that technique iterative process or iterative technique. Okay, so iterative technique is a process of solving or performing repetitive computation using a loop, a while loop, a do-while loop, or a for loop. And on the other hand, we could also solve repetitive computation using the process of recursion. Recursion is the process of solving or performing repetitive computation by using a recursive function. So again, a repetitive computation is a computational task that is repeatedly done or performed. And we could solve repetitive computation using a loop, and that process is called, or that technique is called iteration or iterative process. Or we could use recursion by making use of a recursive function. What is a recursive function? It is simply a function which has a call to itself. Or like for example, if this is the function definition, inside the body of the function, there is a statement that is a function call to itself. So if a function contains in its body one of the statements to be executed is a function call calling itself, we call that function a recursive function. If it contains or if it has a statement in here that calls itself. So that's another technique of solving or performing repetitive computation. Again, repetitive computation can be performed by using the process iteration, which makes use of a loop, and it can also be solved using recursion process, that is, defining and using a recursive function. Now, let's take, for example, the repetitive computation to compute the factorial of a positive integer. So we have in here a function which we call as an iterative function because this function makes use of a loop, particularly a for loop, to perform the repetitive computation. Why do we call this computation, computing for the factorial of a positive integer n, a repetitive computation? Recall in mathematics, if n is a positive integer, then the factorial of n, which is denoted like this, so that is the notation for factorial of n. This is defined in mathematics as simply n times n minus 1 times n minus 2 times up to 1. So that if n is equal to 4, then n factorial is equal to 4 factorial, which is, according to this definition, it is 4 times 3 times 2 times 1. So until 1. So 4 factorial is equal to 4 times 3 times 2 times 1. And so, going back to the question of why is the computation or the problem of finding the factorial of a positive integer n, why is that called a repetitive computation? What is the task in here that is being repeatedly performed? What is the task? The task in here that is repeatedly performed is the task of multiplying by I, where I is from n down to 1. If n is equal to 4, like in this case here, the task that we repeatedly done or performed is multiplying by I, where I is from 4. Okay, so our I is from 4 down to 1. So if we let f to represent the factorial of n, then we would say here f is equal to n factorial, which is equal to 4 factorial if n is equal to 4. And so we can initially set f to 1, and then we would say f gets f times I. So the task of multiplying by I is repeatedly done 4 times. So we initially set f to 1, and then the first time we do this, multiplying by I, is substitute f equal to 1 in here. So that would be 1 times the first value of I in this range is 4. So we would say I times 4. And then that is equal to what? What is f in here? It is 4, right? So the second time this is executed is, this would now be f this time is 4 from the previous value, 4 times the next value of I is 3. So f now becomes 12, 4 times 3. And then repeat this again, multiply by I, and this time, okay, take note that this column here is your f and this column here is your I. We are performing f times I repeatedly. And every time we multiply by I, the value of I is a new value. Like in the first one, our I is 4. On the second, multiply by I is 3. And the third would be from the previous value of 12, value of f is 12. So this is now 12 times 2. That is 24. Okay? So f now at this time is 24. The last one is 24 times 1, and that is still 24. So we perform this task of multiplying by I 4 times. When I is 4, when I is 3, when I is 2, and finally when I is 1. That is why we call this process of computing the factorial of positive integer n as a repetitive computation, because it repeatedly performed the task of multiplying by I, where I is from n down to 1. Okay, so like in this case, times I when I is 4, times I when I is 3, times I when I is 2, and times I when I is 1. We repeatedly do this task for all the values of I from 4 to 3 to 2 and lastly to 1. So we multiply by I 4 times, and in general n times, where n is a positive integer, or n is an element of the set of positive integers. And in this example, in this program, which we call iterative.c, okay, that is what we use as a file name to put emphasis that in this program, we are employing the process of iteration, meaning we solve the factorial, or we compute for the factorial of n using a loop. And since we are using a loop, we call this process iteration. Iteration is the process of solving repetitive computation using a loop. Since it is employing iteration process or iterative process, we call this function an iterative function. Now, let's try to run this program. Okay, so this is now our program, iterative.c. So it has one user-defined function, which we call factorial, and it has only one argument or parameter. N is called a formal parameter. So this is the function definition, and this part here, this one is the function call. So when we input in here n equal to 4, then this is computed. This function call is executed, passing the value 4 in here. And so this formal parameter here will have a value 4. And inside the function, we have two local variables, I and f. I is used as the loop variable that proceeds from n down to 1. And then f is the variable we use to hold the factorial of n. So initially, we set the factorial f to 1, and then we update it 4 times, okay, because this for loop iterates 4 times. When I is 4, when I is 3, when I is 2, when I is 1, okay? That is if n is equal to 4. And by the way, what is this part here? Why do we have a do-while loop here? The purpose of this do-while loop is so that just in case the user inputs a non-positive integer, because our requirement here is that the value of n, the user input value, must be positive integer. And for us to make sure that the user input value for n is positive, we have to use a do-while loop, meaning we keep on asking the user to input a value n as long as the user inputs a non-positive integer. So the only way we exit from this do-while loop is when the user follows our requirement that the user input n should be positive. If it's not positive, like example, if the user inputs 0, the condition here is 0 less than 1. That is true, right? 0 less than 1, that is true. So while true, this would be executed. If the user inputs negative value like negative 3 is less than 1. This is true. Therefore, this is executed again, meaning we ask again for an input value for n as long as the user will not follow what we require, that the input should be positive. If the user inputs a positive value for n now, and positive value is less than 1, that is false, right? So if the user inputs 1, this is 1 less than 1, that is false. And therefore, this do-while loop will be terminated and it jumps to compute for the factorial of 1. So the acceptable user input values for n would be from 1 to greater than 1. So it should be only positive integers, where the minimum or the least positive integer that the program accepts is 1. Okay, so let's compile this. Compilation is successful. Okay, so we run this one now. So this is what we got in the output window. Execution starts in the main function. Therefore, this has the statement, this program computes the factorial of positive integer n according to what we have here. And then it prompts the user to input a positive integer n. Say if we input 0, it will ask again for an input. If we input negative 5, it will ask again. It will not stop asking for user input as long as the user does not follow the requirement that the input should be positive. So for example, we input 4, a positive value, and then we enter. Now this time, the do-while loop is terminated because our n input is 4. It's a positive integer, and therefore, this is terminated and it proceeds to execute this one. So the output is the factorial of 4. So what we display here is the value of n, which is 4, the one we input here. And what is displayed in this position for this conversion specification is the value returned by this function. Okay, so we jump. This is a function call. So we call the function passing the value 4 as the value of n. So this is 4, and therefore this is 4. And it iterates 4 times. When the for loop terminates, the value of f, the latest value of f is 24, and it returns the value 24 to the caller. It returns the value 24 here, and then it is displayed here. Thus, we have this output, 24. The second technique that we can use to solve repetitive computations such as factorial of n is recursion. Recursion, as mentioned already earlier, it is the process of performing repetitive computation by calling a recursive function. When we are going to employ the technique recursion to solve repetitive computation, we need to define a recursive function. And what is a recursive function again? It is a function that calls itself. Let's open the second program, where in this program we employ recursion. So again, when we are going to employ recursion to solve this repetitive computation factorial, we need to define a recursive function, a function that calls itself. So before we could define or we could write a recursive function, we need to recall the recursive definition of this problem, factorial of n, in mathematics. So let's recall in mathematics, if n is a positive integer, n factorial is defined as n times n minus 1 times n minus 2 times up to 1, right? So the recursive definition now in mathematics for factorial of n is, it has two cases. If n is equal to 0 or n equal to 1, what is 0 factorial? What is 0 factorial or 1 factorial? 0 factorial is 1, right? And 1 factorial is also 1. So these two are the same. 0 factorial is equal to 1 factorial, which is equal to 1. The first case is, in the recursive definition of factorial of n, is if n is equal to 0 or if n is equal to 1, then the factorial of 0 or 1 is 1. It returns 1. Factorial of n is equal to 1 if n is equal to 0 or if n is equal to 1. And the second case is, if n is greater 1, what is the factorial of n? If n is greater 1, say for example, if n is equal to 4, 4 factorial is equal to 4 times 3 factorial, right? And 3 factorial is equal to 3 times 2 factorial. And 2 factorial is equal to 2 times 1 factorial. And 1 factorial is equal to 1. Okay, so you have found the value of 1 factorial to be 1. So this is 1. You substitute it here. So 2 times 1, 2 factorial is 2. Substitute this one in here. This is 2. So 3 times 2 is, this is equal to 6. And this value here, you substitute that in this part. 6, 4 times 6. Therefore, 4 factorial is equal to 4 times 6, which is 24. So this is what we call a recursive process. The word recursive comes from the word recur. Recur means to reoccur or to happen again. Recur. So in this recursive process, what happens again? What is that scenario or what is that computation that happens again or that is being repeatedly performed? What is that? It is the computing for the factorial of n. Our original problem is finding 4 factorial. This problem of finding 4 factorial leads us to find 3 factorial. So we have a problem that leads to another problem which is the same. Okay? The problem here is finding the factorial of 4. And solving this 4 factorial, we encounter the same problem, finding the factorial but of a different value, which is 3. And this problem of finding the factorial of 3 leads us to the next problem of finding the factorial of 2. And we cannot solve this one yet because we need to find the value of 3 factorial first. And so we find 3 factorial. We solve 3 factorial. Solving 3 factorial, this leads us to another problem, which is solving for 2 factorial. And so we cannot compute that one yet because we need to find first what is 2 factorial. So the problem of finding the factorial of a value is it recurs again. So 2 factorial now, the next problem. Solving this leads us to 2 times 1 factorial. So we cannot again solve for that because we encounter again the problem of finding the factorial of another value, which is 1. And so before we could solve that, we need to solve this. So we solve 1 factorial. What is 1 factorial? It is 1 times 0 factorial. And 0 factorial is equal to 1. Or you could stop in here because the definition tells or says that it is equal to 1 if n is equal to 0 or 1. The factorial of n is equal to 1 if n is equal to 0 or 1. So we could say here 1. Now that we know that 1 factorial is 1, we substitute that 1 here. So this becomes 2 times 1. So now we can get the value of 2 factorial. We have solved it already. This is equal to 2. And that value, we substitute it here. This is now solved. That is equal to 2. And 3 times 2 is 6. So this one is solved now. It is equal to 6. And then we substitute this value here. So this is now solved. The value of this is 6. And 4 times 6 is 24. Therefore, this has now a value, or this is already solved. And that value is 24. The process that we employ here to solve the factorial of n is called recursion. And the task that keeps on recurring is the task of finding the factorial of I, where I is from n down to 1. That is the task. This is the task that we keep on doing or performing for finite times. Finding the factorial of I, where this I is from n down to 1. So this is what we illustrated a while ago. The first task is done here, finding the factorial of 4. And then the same task is done here, finding the factorial of 3. And then the next time it is done, it is in here, finding the factorial of 2. And then the last time it is done is here, finding the factorial of 1. So in summary, the recursive definition of the factorial of a positive integer n is defined in mathematics this way. N factorial is equal to 1 if n is equal to 0 or n is equal to 1. And if n is greater 1, this one is equal to n times n minus 1 factorial. Okay? This is the definition of n factorial if n is greater 1. Now take note, we call this the recursive definition of factorial of n in mathematics. Recursive because finding the factorial leads us to finding again the factorial. So the same problem reoccur or recur in here. It's just like when there is an unfamiliar word you encounter, you try to look up in the dictionary the definition of such unfamiliar word. When you look at the definition in the dictionary for that unfamiliar word, hoping that you will get to know what that unfamiliar word is, the meaning of that word, when you read the definition, you encounter another unfamiliar word in the definition. And so you cannot fully understand yet the first unfamiliar word because in the definition of that first unfamiliar word, you encounter a second unfamiliar word. And so you look up the dictionary again for the meaning of the second unfamiliar word so that you can understand the first unfamiliar word. And then, if in the definition of the second unfamiliar word, you encounter again a third unfamiliar word, then you keep on looking for the meaning of the unfamiliar word. So the task of finding the meaning of an unfamiliar word keeps on recurring or repeatedly occurring until such time that when you read the definition of the unfamiliar, the latest unfamiliar word, there is no more unfamiliar word. And so you go back to understand the previous unfamiliar words until you arrive at the first unfamiliar word. So if n here is 4, finding 4 factorial leads to 4 times 3 factorial. We cannot solve this one yet because we encountered the same problem of finding the factorial. So by this definition again, we find 3 factorial, which is 3 times 2 factorial. And we encounter another factorial problem. So this is pending, and we compute for the next factorial is 2 factorial. And by that definition again, this is 2 times 1 factorial. And so we have another problem of finding the factorial. So this is pending. And when we find for the factorial of 1, according to this first case, it is equal to 1. So that's the time you go back to the previous problems. This 1, 2 times 1 is 2. So it's no longer pending. It is now solved. Substitute 2 here, the value of 2 factorial, 3 times 2. This is now solved. It is equal to 6. And then substitute that value in here. This becomes 6. 2, 4 times 6 is, this has now a value, and that value is 24. So that is the action of recursion. So how is that we come up with this function from the definition? We call this one now, this function, as a recursive function. Because again, what is recursive function? It contains a call to itself. As you can see here inside the body of the function factorial, we have here a call to itself. This is the function call, calling itself. So that's why we call this a recursive function, because it contains this one in here, a function call calling itself. How did we come up with this function? From the definition, take note there are 2 cases. We call this case the stopping case, or some books would call this the base case. The base case or stopping case. Why do you think it's called stopping case? Because take note that this is the value of n that will cause the repeated solving of factorial to stop. Since n is now equal to 1, it stops. Notice that there is no more on the right side a factorial symbol. So we are done solving the factorial. Okay, there is no factorial. We are not led to compute again for a factorial in this case. But in the case when n, these 3 cases, 4 factorial, 3 factorial, and 2 factorial, where n is greater 1, in this case n is 4, it is greater 1. In this case it is 3, n is 3, it is greater 1. In this case, n is 2, it is greater 1. So for all these cases, when n is greater 1, we are led to compute the factorial again. This is what we call, this part here, the second case, we call this the recursive case. So take note that a recursive definition has 2 cases. The stopping case, or called the base case. The second is the recursive case. What makes this definition a recursive definition is the presence of the second case, which is the recursive case. So that's why it is recursive definition, because it has a recursive case. But of course, every recursive definition needs to have a stopping case, because if there is no stopping case, then we call this one now infinite recursion. Infinite recursion is a recursion that has no stopping case or base case. What it has is only recursive case. So infinite recursion, it will not stop. It will keep on finding the factorial of a number. It will not eventually stop because there is no stopping case. If there is no stopping case, then that is called an infinite recursion. And of course, that is something that you should avoid. This is not a good programming scenario. So by all means, you have to avoid infinite recursion. Looking at the recursive definition again, it has 2 cases. The first one is called stopping case or base case, and the second one is called recursive case. So when we now write the recursive function, which is this, you will just say, what is the return type of this function? It returns 1 in here, and this would return 1 also. Okay, eventually, since n is a positive integer, multiplying positive integers would result to what product? Also a positive integer, right? Like for example, when you say 4 times 3 times 2 times 1, multiplying integers will result to a value which is type integer also. Like in this case, integer 24. So this function, factorial, has a return type integer, and the formal parameter n is also integer because that is what we required in here, that n should be positive integer. Okay, so this is integer and it returns integer, and this is the first case, the stopping case. The meaning of this case here in the mathematical definition is if n is equal to 0 or n is equal to 1, then this function will return the value 1. So you can add in here or n equal to 0. And then instead of having that one there, you enclose everything in parentheses. But of course, if you can just use equal to 1, okay, you can omit the equal to 0. So this would be enough, saying if n is equal to 1, then return 1. And then this function will perform this computation if n is greater 1. So else is if not equal to 1. Now, we don't have to put else if, although you could do that, else if n is greater 1, okay? You could do that because that is the specific condition for the recursive case, this one. The specific condition is that if n is greater 1. But the reason why we can omit this part here is because we already, before we call factorial in here, we already filtered, make sure that the user input n is positive by using this do-while loop. If you are not using do-while loop, and there is a tendency that the user inputs a negative value, and so it goes here, factorial, for example, the user inputs negative 4 for n in here, and since you are not using, for example, the do-while loop, then that is not prevented from happening, the acceptance of a negative integer. So in that case, factorial of negative 4, that is if the input value in here is negative 4. So if that's the case, that this could be negative, then you need to put that if here, if n greater 1, so that this will only be computed for positive integer, because there is a chance, a possibility that n is not positive because you did not use a do-while loop. You did not make sure in here in the input that the input should be positive. But since we make sure already from the main function, we already make sure that the user input for n is positive by using this do-while loop, then we are safe to say just the else. We don't have to check if it is positive because it is already made possible in here that the input should be a positive integer. So no need to put the filtering here or the checking if n is greater 1. Okay, no need for that. And so if n is greater 1, then we are to compute this expression n times, we denote this as factorial of n minus 1. If we're going to rewrite this recursive mathematical definition and substituting n factorial for the function called factorial of n, if we let that expression to be replaced by that function call, then rewriting the recursive mathematical definition, we would say, replace this one with this function call. We would say factorial of n is equal to, or the factorial of n function call would return 1 if n is equal to, we can remove that 0 if n is equal to 1, and this one would return n times n minus, if n factorial is represented by that function call, then n minus 1 factorial is represented by the function call factorial n minus 1, right? So we replace this part here with the function called factorial of n minus 1. That is why in the recursive function in here, we have this one. If n is equal to 1, okay, this part here, then the function called factorial n would return 1. And the second case is if n is greater 1, okay, this one here, if n is greater 1, or you could just say else, because the meaning of else is that n is greater 1. The function called factorial of n would return this expression, or the value of this expression, which is, it would say here, n times factorial of n minus 1. Okay, this one here. Okay, let's run now this second program, which employs recursion. Compile, run, input 0. It doesn't accept the input 0. Say negative 5. It doesn't accept negative and 0. So if we input 4, it accepts it and it returns 24, just like in the first program that employs iteration. So notice that these two programs, Iterative.c and Recursion.c, these two programs solve the same problem, the factorial of positive integer n. And we make sure that the user input is positive by using a do-while loop here. The first program that employs iteration, we make use of a for loop to solve the factorial of n, while in the second program, we make use of a recursive function, a function that contains a call to itself, and therefore we employ here the technique recursion. Let's trace the second program. If the user inputs here 4, therefore n is equal to 4, then this function call is factorial of 4. This is the first call. So the first function call is factorial of 4. And what it returns, this is 4. So this is false, and so this is returned. It would be n is 4. So this n here is 4 times the factorial of 3. That's 4 minus 1. So this is 3. And this first function call does not give us any resulting value yet because we need to find next the factorial of 3. So this computation is like pending. So we make another call. We make the second function call. And this time, our second function call is factorial 3. This one here. And this would return to us, again, this expression, which is 3 times another function call, calling factorial, passing the value 2 for n. And so this second function call does not give us any resulting value because this computation is again pending, because we still need to find what is the factorial of 2. So the third function call now is factorial 2. And again, n is greater 1. So it returns to us, and this time is 2. This would return to us 2 times factorial of n minus 1. This is 2 minus 1 is 1. Once again, the third function call, this does not return to us any resulting value because in the computation, we still need to find the factorial of 1. So this right side expression here is again pending. And so this leads us to the fourth function call, which is the factorial of 1. And this time, the value of n is equal to 1. So the first condition here in the if statement becomes true since n is already equal to 1. And so it returns to us the value 1. So we arrive now at the stopping case, which is this one here. We call this the stopping case of the recursive function. And this part here is, we call this the recursive case. Now that the fourth function call, factorial 1, has a value, Then we substitute this value to this part here in the previous, the third function call. So this has a value now, which is 1. And so this is no longer pending. We could compute 2 times 1, that is 2. So the third function call returns a value 2. And this is substituted to this function call factorial 2. And so this has a value 2. 3 times 2 is 6. So this second function call has a return value 6. And then this value is returned here. So this has now a value 6. 6 times 4 is 24. So 24 is the return value of the first function call factorial 4. So factorial 4, which is this one, the first function call will have a return value of 24. That's why in the output that we saw earlier, the output here is the factorial of 4 is 24. Okay, so before this value is displayed on the screen, this is the whole process that the computer underwent so that it could return this value 24. So this is what we call again the process of recursion, making use of a recursive function which has a stopping case and a recursive case. What makes this process a recursive process? Because of this recursive case. If there is no recursive case, then we cannot call this a recursive function and we cannot call this process recursion. But if it has only recursive case and no stopping case, then what happens is that this would result to infinite recursion, which is not a good programming practice, and that is something that you should avoid. So for a normal recursive function, for a normal recursion process, there must be these two cases, the stopping case and the recursive case. Now take note that in the process of recursion, it is described as like going through this process. The original problem is factorial of 4. This one, the original problem, factorial of 4. To solve that, you encounter another problem which is smaller because the value is getting smaller. From 4, the value of n now becomes 3. So you went through the same problem, but this time it is a smaller problem because n is equal to 3. And solving for factorial of 3, you encounter the same problem of finding the factorial, but for a smaller value too. So the problem gets smaller. And then solving for factorial of 2, this leads you to another problem, same problem of finding the factorial, but the problem gets smaller. This time you are looking for factorial 1. And then finally, for factorial 1, it doesn't result to a recursive case anymore. You arrive now at the stopping case. So this has now a solution, and that solution, you pass it back to the previous problems, and you finally solve the original problem, which is the factorial of 4. And this is now a value which is 24. So this is the process that best describe recursion. If recursion is infinite, what happens is that the process is described as like this. Infinite recursion. The problem does not get smaller. Okay? It's constant. It's always big. And it never stops because there is no stopping case. This is the infinite recursion and this is the normal recursion. This is the normal recursion. This is infinite recursion.